Classify the following molecules as polar or nonpolar. We've got three molecules that we're going to look at in this question, and we're going to do them one at a time. These types of questions where we're classifying a molecule as being polar or nonpolar are kind of sneaky difficult because there's a lot of information you need to consider to make your final judgment. Okay, we're going to walk through it step by step, and we'll start with water. Okay, the first thing you want to do when you think about this is you want to get to where you know the shape of the molecule. Okay, you might be able to jump straight from the formula to the shape. You might need to go through a Lewis structure first and then draw a shape based on that. So let's practice drawing a Lewis structure first, and then we'll do a shape. So for each case, we're going to put our Lewis structure here. For water, that's going to look something like this. Okay. Based on this Lewis structure, I've got 4 electron groups around the central atom. 2 of those are bonds. That's going to give me a molecular shape that is bent with 109-degree bond angles. Okay. Once we know the shape, we need to think about the bonds themselves and whether those bonds are polar. If I have all nonpolar bonds in my molecule, my overall molecule is going to be nonpolar. So that's kind of the easiest case. Okay, we want to then look at bond polarity. So let's see here. In bond polarity, the way we need to think about it is we need to know electronegativities. So let's look at the electronegativity of oxygen. We can look that number up, and that number is equal to 3.5. Hydrogen, we can look that up, and that's equal to 2.1. Okay. Knowing those electronegativities, we can draw bond dipole arrows. Okay. So we're going to combine that information here, bring it up, and draw our bond dipole arrows. The arrows point from the less to the more electronegative atom within the bond. So for this bond here, that's our bond dipole arrow. For this bond here, our bond dipole arrow is going to be in that direction like that. This is why shape is going to start to matter, because the shape dictates how these arrows are oriented in space relative to each other. Okay. Based on this information, then we need to ask ourselves, okay, do these bond dipoles cancel in space or not? If they cancel, it's going to be overall no dipole for the whole molecule. If they do not cancel, then the molecule will be polar. Okay. In this case, you can kind of see they're both pointing in an upward direction, so they're not going to cancel in that way. So for this molecule, the bond dipoles do not cancel. Okay. Therefore, the molecule is polar. All right, let's try this next one. Silicon tetrafluoride. The Lewis structure for this is going to look something to this effect, with lots of lone pairs. All the fluorines have 6 electrons around them, 3 lone pairs each. Okay. The shape of the molecule, I have 4 electron groups. All 4 of them are bonds. We know that shape is going to be tetrahedral. The way that I draw a tetrahedral requires a wedge dash drawing like this. Okay. I'll give the dots. Okay. Bond angles are all again 109 degrees. Okay. Once we know that, we need to think about the polarity of the bonds. So we need to know electronegativity values. Electronegativity of silicon, we can look that number up. It's 1.8. Fluorine is 4.0. These are definitely going to be polar bonds because there's a huge electronegativity difference here, right? The bond dipoles are going to point from the less to the more electronegative, so they're going to point from silicon to fluorine for each bond. So there's a bond dipole for each of these bonds that's parallel to the direction of the bond in space. Okay. So at this point, we're going to assess overall, do all of these arrows cancel each other out or not? First of all, they're all the same type of arrow. Each is a silicon-fluorine bond. They're all the exact same type of bond. So then we have to think about how are they oriented in space. If we remember the whole point of a tetrahedral shape, it's that all 4 groups are spread as far apart as they can be in 3D space, all in opposite directions. So Effectively, yes, they will all cancel. You can convince yourself of this by building a model or going online and looking at a simulation, or you can just remember a tetrahedral means they're all pointing into separate directions, and so they're going to cancel if they're all the same like this. Okay, so for this case, bond dipoles do cancel in 3D space. Okay, that means that there is a non-polar molecule. Since there is no overall polarity because they all cancel. All right, let's look at this last one, SO2. We need to draw a Lewis structure for this first. This one's a challenging Lewis structure. It'll take a little bit of guess and check maybe to get it correct. But you can get a structure that follows the octet rule for all three of the atoms and has the correct total number of electrons, and that Lewis structure will look something like this. Okay, we can draw the shape based on this. There's three electron groups. This one, and this one. Two of them are bonding groups. So that means our shape is going to be bent with a 120-degree bond angle. It's going to essentially look like what I just drew. Okay, that's the shape of the molecule in 3D space. We need to look at the bond polarities. To do that, we need electronegativity values. The electronegativity of sulfur is 2.5. Oxygen is 3.5. Means our bond dipoles are going to look like this. Okay. Pointing along, that one's kind of tough to see, along the bonds in these directions. Okay. We ask ourselves, do these these bond dipoles cancel out in space? They do not, because they're not pointing in opposite directions. They're both pointing down to some extent. Okay, so bond dipoles don't cancel. Therefore, the molecule is polar.